Welcome to everybody to today's lecture. Today we're going to be continuing to talk about linked lists. Particularly, there are just two things left that I really want to talk about. That is the insert and the delete function. What you'll see here as we get into it is the insert function will borrow a lot of the same functionality from our print list. Our print list function is what we talked about at the end of the previous lecture. So even though it's new, we've already really discussed all the concepts. It's just putting them together in a different order. As far as delete goes, delete's pretty straightforward. So when we cover that, it will only take a few minutes. What you'll notice if you looked at this code already is that we have two versions of the insert function. One insert that just inserts a new node at the end of the linked list, and then we have a second version that maintains the sort order. We don't need to cover the version that maintains a sort order. You don't need that for the lab. So we're going to cover the first version first, and if we have time, I'll produce another lecture and we'll cover the one that maintains a sort order. Okay, so it's not critical that we cover that. So if you see that in the code and then we just never talk about it, don't worry about it. You can certainly uncomment it. You can look at it. There's very little that changes in that function. And if you have questions, you can always shoot me an email or something and let me know, and I can help you out. So where we left off at the last lecture, we introduced what a linked list is. We talked about some of the pros and cons, why we'd want to use a linked list over something like an array. And then we looked at some code. And we start off with our linked list conversation, excuse me, using a self-referential structure. Okay, one of the members has to be a pointer to a variable of the same type. Okay, so this is a pointer. We'll call it next node, and it's the same type as this struct char node. We also have one member to hold the data. Okay, so if it references another node but it doesn't hold any data, it's not any good to us. So this is by no means a hard and fast format for nodes or for linked lists. You can add other members to it, but this is just the simplest way for us to talk about it. We use the type definition. So we called this structure char node, but then we created a type definition right here, and I call it node. So everywhere in the code, excuse me, we're going to refer to that structure using our node shortcut. You can see here we have our print list, our insert, and our delete. And then in our main function, what we did last lecture was we essentially manually created two nodes and then linked them together. And then we call our print list function to print those. So just like any other variable that we use malloc with, we use malloc, we use the size of operator. This is just a struct. We make sure to typecast it, and now we have a pointer of a node type in the root variable. Keep in mind with a linked list, we care about where the root is. We always care about where the very first node is in our linked list, and we want to keep track of that with a pointer because we're dealing with memory addresses. Remember that malloc returns either a memory address or a null value. You won't see me check for any null values in here really. A couple of the functions the author does, and I didn't bother to change it. It is important that we do, but because I want to just focus on the core of the linked list, we won't worry about some of that finer detail here. Once we malloc the memory for it, we have a pointer. The value of that root variable then is the memory address that represents the first node in our linked list. Linked lists are linear, so one node is going to be created, and then we're going to link another node to it. And then if we create another one, we link another node to it. And we just do that as many nodes as we need for our linked list. So we have it created, and now we update the members. Okay, at this point in time, if we go no further than this line of code here on 23, this is the only node in our linked list. So we update its member to something arbitrary because that member is a char type. We're going to hold char data in it. And we set the next node member equal to null. Remember, this is absolutely critical that we understand and update accordingly that next node member. The next node member on the last node in the linked list needs to be equal to null. That's how we're going to find the end of a linked list. The print list function uses it, and then the insert function will use it, as well as the delete function when we talk about it. Okay, so right now, with these three lines of code, we have a one node linked list. We move on to line 24, and we malloc memory for a second node. Okay, so very similar syntax. I store it in a variable called second, update the data member. Now we update its next node member equal to null. And we do that because we know that the second node is going to become the last node in our linked list. So up through line 27, we have two nodes, but they're not linked together. Okay, this one stands alone because its next node member is equal to null, and this one stands alone because its next node member is equal to null. So in order to link root to second, or second to look, depending on how you want to think about it, we need to update that next node member. So on line 29, I say that the next node member from that root node is going to have a value of the memory address from the second. Okay, so here is the memory address. We assigned it into the second variable. That's a pointer that represents that second node. We assigned it the value to the next node member, and now we've created the link. So this is what creates that link. Next node member for the second node is still equal to null. So when we print list, when we traverse this linked list, we can look at each node, we can look at each next node member, and we're going to walk those members until we find one that has a value equal to null. And when we see this print list function, you'll see that now we print off our linked list, which is CA, and then null. Okay, so it worked exactly the way we wanted. If I were to forget this step, okay, so let's say I comment out line 29 so that I'm not creating the link. Run it again. Okay, let me clear the screen. Okay, we just get C. And why did we just get C? Because C is the data member. That's the value in our data member for our root node. When we do the print list, we always start with the root node because we want to traverse every single node in our linked list. But because this wasn't linked, right, we skipped this step, or I took this step out, then there was only one node. It entered the node, it checked the next node member, it saw that it was equal to null, and it stopped. Okay, so it's important that we make sure we create the links and that we essentially, just like when we null terminate a string, we want to make sure that we null terminate, we have the next node member in our linked list equal to null. Quick review, how does print list work? Well, we call print list. Print list has one argument, it expects a pointer, so memory it's a pointer, so it expects a memory address. Root's a pointer, so its value is a memory address. First thing we do is we check if it's equal to null. If it's equal to null, then we have no linked list, so we can stop. We print off that it's empty and we move on. If it's not equal to null, we'll enter this else branch. We'll print off some informational things, the list is, and then we'll start our loop. Okay, our argument then is a memory address. This is the value of that root node. So as long as that's not equal to null, we want to iterate. It's not in this case because we know root has a memory address. So we access the data member from that node, print it off, and then we set current pointer equal to current pointer's next node. We iterate again. Is that equal to null? Well, in this case, after all these lines of code execute, the next node member on that root node is equal to the value of that second variable. So it's a memory address, it has a value. So we iterate again. Now we're iterating on the second node. So we print its data member, we set current pointer equal to current pointer's next node, and we go around and check the condition. Okay, in this case, next node was equal to null. So we just set the current pointer, we set current pointer right here, we set that equal to null. Is current pointer not equal to null? No, it is equal to null, so that's no longer true. So our loop breaks, we print null, and now our function is done. And that's how we get that to print C, what was it, C, A, and then null. All right, when we look at the insert function, you're going to see that this while loop is going to use very, very similar logic as we do here. Okay, what is this doing? This is allowing us, this is walking every single node in the linked list to find the end of the linked list. Once we find the node whose next node member is equal to null, we're at the end of the linked list. At least the logic in our program is going to tell us that we found the end of our linked list. Once we reach that, we're done. So we're done with whatever we're doing. In the case of print list, we're done printing. If we kept going and we tried to print a memory address from a node that actually wasn't a part of our linked list, or a memory address that wasn't part of our linked list, we'd probably get a segmentation fault. When we insert, we probably would get it to insert, but it wouldn't actually link to our linked list. So that'll cause us plenty of issues. So it's important that we understand this and that we use it correctly in our code. All right, so let's take a look at a few slides here just to get our minds around what we're about to talk about, and then we'll look at the code, and then we'll be done for this lecture. So we want to insert, and like I said, this is a pretty simple insert function in that we're not going to worry about inserting in any particular order. Okay, so the logic, the overall logic of this, of all this code here, is that we want to walk to the end of the linked list. We want to find the last node. So we want to find the next node member that is equal to null. We want to create a new node and then link it. So we're doing logic from our print list and then the same logic that we just covered in our main loop. or our main function. We'll change that code in the main function here once we implement our insert function, but it's the same exact thing. We're just pulling it into this one function. Big picture then, we're going to have a couple of, well, first of all, we're going to introduce our second level of indirection, right? So node, we'll go back and we'll just review that. I'm going to discard this change. Hold on one second here. I got to pause. Something just came up. Okay, apologize for the little abrupt change there. I just had to make a slight change to the code. So if you've downloaded the slides before the lecture, please download them again because I did have to change them a little bit. What you're going to see now, what you should see in your code, if you're not looking at this code or you don't see this in your slides, please again just download the correct version. You'll see the two arguments for our insert function. So here's our second level of indirection, and then here's the value that we want to insert. And so when we call this insert function, we're gonna pass the value of the root node and the value we want to insert. And then this node itself, this function itself, will take care of everything else. It'll create the node, it'll link it up, it'll update the data members, and it'll be done. This is our second level of indirection. Now, it's not quite as critical that we have it here, talking about this insert function that does not maintain a sort order. So we don't really use it. You won't really see the value of it here. Take a look at the second version of it if you get a chance, if we don't cover it in class, and that you'll see why we have to do it that way. And I'm sure we'll talk about it. We'll just go over it real brief as kind of a final wrap-up lecture on linked list. Once we get past the arguments then, okay, so when we call this function, we're going to provide the root node, the value of the root node, so a memory address, and then the value we want to insert. We have 3 pointers, and we're going to talk about each one of these here. So here's our 3 pointers. We have a pointer for the node that we're going to create. We have to have a previous pointer and a current pointer. And hopefully you'll see, it'll be clear once we get into the core of this function, the while loop, why we need to keep track of a previous and a pointer. Okay, here we do have a little bit of error checking. Okay, so new pointer, a pointer that's going to be the new node to our linked list. We allocate memory for it right here, and then we have 2 branches of logic. Okay, if our new pointer is not equal to null, we enter right here, and this is now where the meat or the core of this function is. Otherwise, we got a null value because malloc only returns a memory address or a null value. It says it's not inserted, and we can't do anything. So we're going to assume that in almost all situations, we're going to get the memory we want. We're going to do 2 things here. Just like we did in the main function, the code we just looked at, the code we created in the last lecture, we're going to update the data member, and then we're going to set the next node member equal to null. Now, again, this is critical because what we're doing in this function is we are just simply inserting a new node at the end of the linked list. So this new node has to have its next node member equal to null, because that's how we're going to find the end of the linked list. Okay, get rid of some of this stuff here. Okay, now we've done that, so we've updated those 2 members, so we have a new node, and the new node is set up. So at this point in time, the only thing we have left to do after those 2 lines of code execute, the only thing we have left to do is find the end of the linked list and then link it to this new node. Okay, so we need to set up our previous and our current pointers. Previous pointer equals to null, because at this point in time, this is going to have the value of our root node. We're going to start at the very beginning of our linked list. So there is no previous pointer, there is no previous node. You can think of these pointer values, previous and current, as previous node and the current node that we're looking at. Okay, so at this point in time, we're starting at the beginning, so there is no previous. So we set it equal to null. We set current pointer equal to our start pointer. Okay, we have our second level of indirection here. So in order to make this assignment work, current pointer is a pointer to a node. Start pointer is a pointer to a node. Okay, so we need to make sure that we do reference it once in order to make it a pointer to a node. That way we can assign its value to our current pointer. These are memory addresses, so we don't want to use this value here. We don't want to use the value of this argument, because if we change that, then that would change where our root node was pointing to. So we want to temporarily store it in a node, a local scope variable inside of this function here. Okay, so that's what we're doing. So at this point in time, I'll try not to mark this up with these little red dots. At this point in time now, we have a node ready to go. we have two pointers to help us traverse our linked list, the previous and the current. Previous is equal to null because we have no previous, and our current is set up and pointing at the root of our linked list. So now enters the while loop, and this while loop is going to look almost identical to the loop in our print list function. Okay, so while current pointer is not equal to null, enter the loop. Now, instead of printing off the member and then walking to the next node, we're simply going to update the previous pointer equal to the current node, and then set the current pointer equal to the current pointer's next node. Okay, so this line of code here, this is exactly the same. This is the code that we need in order to walk the linked list. Okay, because once current pointer is equal to null, we found the end of the linked list. But there lies the problem. Because once current pointer is equal to null, once we find that node whose next node member is equal to null, and we set that value to current pointer, so current pointer takes a null value, it's null. We can't do anything with it. We don't know when it's null. We don't know what its value was before in that last iteration to find those nodes in memory. And that's why we have this previous pointer. Okay, so when this loop breaks, we're going to iterate, we're going to walk all those nodes, and once current pointer is equal to null, current pointer helped us to break the loop, to find the end of the linked list, then it's worthless. Now previous pointer has the value that we need. Previous pointer, when this loop breaks, previous pointer, its value is going to be the last node in the linked list. Okay, so when we break there, previous pointer is a node. We can access its members, and we can say that its next node member equals the memory address of that new pointer. Okay, so right here. That's the same thing we did in our previous code example, where we linked that root to that second node. Okay, once we've done that, we're done. We've created the node. We've traversed the linked list to find the last node. We've linked the two. The node that we created has a null value, and we're done. So this function can terminate, return, and we can go about whatever business we were doing in our program. All right, so that's a high-view overview of the function. The next few slides just break that up piece by piece. Okay, so we won't really spend any time on those because we've already done that. Okay, so what I'm going to try to do then is let's go through the code, and then we'll come back and I'll just try to diagram it one more time to hopefully clear up any ambiguities that I may have brought. Okay, so here's the code. Here's our insert function. It should be exactly the same as what we just went over in the slides. How we're going to change this then is we no longer need these other nodes. The second node, okay? We're going to leave the first one because one of the, I guess you could say, flaws or limitations in this function is that it doesn't allow you to just create the very first node. The very first node you have to create. These functions assume that we're starting with a memory address. Okay, so we're going to create the root node. I'm going to call it root. That way in my mind I know that I'm still, this is the very beginning of my linked list. But now instead of creating the second one manually, allocating the memory, updating the members, and linking it, we went over that in that function. We know that our function does that, our function does this piece, and it also does that. So we no longer need that. So how do we use it? Well, we can look at the prototype. It's right above us. We call insert. We have a pointer to a pointer. This is a pointer. So we need to use the address operator on our root node, and then whatever value that we want to insert. Okay, that's it. So we just took all those lines of code, that 4 or 5 lines of code, and we created it or condensed it down to 1. Of course, the function's a lot more, but that helps to organize and modularize our code a lot better. So let's see here. Let's go ahead and just make that change, and we'll compile and run the program and just verify that it works as expected. And there it is. Okay, the list is C, which we knew is our root node, and F, the one that we just inserted, and then null. So we know that it created it, and it followed each node, the 2 nodes in the linked list, on the end null terminated next node member, and everything ran perfectly. Excuse me again, we got a little bit of a cold this week. So if we look at the function here, we look at this code, let's see, let's go back and look at it in the slides, because this is now everything that we just covered. So I'm just going to pause for a second and blow my nose. I'm sorry for all the interruptions today. Okay, so what we have in our code is we had, and I'm going to shortcut some of this just so I don't have to write so much, but we said we have previous pointer and we have our current pointer. And previous pointer when we initialized it, so after we entered that if branch, we said previous pointer is equal to null, and current pointer equals the memory address of root. Okay, so let's say that I'm going to use the blocks to represent the nodes. We have a root node. Let's remember was A, and at this point in time, it's pointing to a null value. So because we passed this memory address, and I'll just use, create something completely arbitrary here. We pass that memory address into that function. We initialize our current pointer to point here. Okay. What we want to do now is we want to insert. So after we've entered the if branch, we know we have the memory for our second node. Right? We've malloced the memory for that. We updated the data member, and we set its next node. And I'm going to represent that arrow. That's going to be my next node member. Okay, and so it's pointing to a null value as well. Right, so now once we get to this stage in the function, the only thing that's left to do is walk to the end of the linked list, identify the next node member that's equal to null, and link it to here. So current pointer, our loop, is while, we'll just call it C pointer to shorthand it even more, is not equal to null, right? Well, it's not equal to null, we're going to iterate. And inside that loop then we set previous pointer equal to current pointer, and current pointer is equal to current pointer next node. Okay, so at this point, this is our current state right over here. Current pointer is equal to this memory address. So we enter in, we set previous pointer equal to current pointer. So we can get rid of this null value. And now at this point in time, they're both pointing to the exact same location. But now we set current pointer equal to the next node member of our current pointer. Well, this is our current pointer, it's our root node, and its next node member is equal to null. So what we've just done is, if I can erase it, yep, current pointer now points to the null value. Right? We just made that change in assignment. So we loop around and we check again. Is current pointer equal to null or not equal to null? Well, it is equal to null. So the loop breaks. The last thing we have to do now is make that assignment operation to change our current pointer next node member and point it to our new node. So let's say that this has its own memory address of something arbitrary, and we assign current pointer next node member, when current pointer is equal to null, it's null. We no longer have, it's more or less worthless to us because we can't do anything with it. We can't create a node from it or access any members because it's null. So it's a good thing that we kept track of the previous pointer. What's the value of previous pointer? Well, if we trace our arrow, we know that previous pointer has the memory address for that root node. So now all we have to do is say, well, we found the end of the linked list. We know that the value, the memory address in our previous pointer is the last node in our linked list. So we update its next node member, and instead of pointing to null, it points to our new pointer. Okay, and that was our third pointer. And I guess I could draw one more arrow. This is getting a little bit condensed, but remember when we entered into that branch, we had we malloc memory for that new pointer. So when we update the next node member of the previous pointer's next node, we set it equal to that memory address. And now it's linked. So now we just created the link. This node links to this node, and this node has its next node member that's equal to null. Okay, so that gets a little, I think it gets a little confusing, and oftentimes on campus we'll spend an entire day just going through some of these examples, especially on a dry erase board where there's a lot more room and it's a lot easier to see. So go through this, let me know if something I've said does not make sense, and I'd be more than happy to either try to answer your question over email or do a Skype or Google Hangout or something so we can talk about this in person. We could certainly try a dry erase board session if we needed to, but that might prove to be a little bit challenging. Let's take a look here. We'll get rid of this. That's the end of the slides. As far as no, I guess it's not. We got a couple more to go. And so, as I said, then the next lecture, what we'll do is we'll pick up and we'll just talk about deleting. So it's the last function here. It looks like a lot, but it really isn't that bad. Again, a lot of the function, a lot of the logic is just going to borrow from the previous code. The only thing that we're going to add into it is that we need to free some memory. And then we also have a second version of our insert. And I'll run you through that. We'll talk about it. But it's not critical for the lab and it's not critical for the final or anything. So it'll just be to help further our understanding of linked lists, and hopefully by the time we walk through this, this code's even more clear. Our original insert function and then the delete function will be, I think, even clearer. So we'll probably talk about this next and then delete, and then we'll call it an end to our linked list talk. So let me know if you have any questions.